This video provides an introduction to chemical reactions. As we know, chemistry is the field that studies matter and transformations of matter, and one of the quintessential ways that matter can transform is through chemical reactions. Okay, so when we think about a chemical reaction, there's various ingredients that we have to consider. The first one is that you're going to have a set of reagents and a set of products. Okay, so you will have a reagent or a set of reagents, and that turns into a product or a set of products. And again, we have to specify quite well what those are. For example, we're going to use here the combustion of methane to illustrate this point. Okay, methane can burn with oxygen to generate CO2 and water. Okay, so right here we have clearly specified what the reagents of the reaction are: methane and oxygen, and then what the products are: CO2 and water. Now, for the reaction to be complete, you actually also need to specify the physical states, the states of matter of each one of the reagents and product species are. Okay, so in this particular reaction, under ambient conditions of temperature and pressure, then methane is a gas, oxygen is also a gas, and then CO2 is a gas, and water is a liquid. Right, so again, these physical states have to be denoted for each one of the species. Now, there's only a couple more that we have to consider. Here we have gases and liquids. The only other two possibilities that you have are either solid or a solid in an aqueous solution, right? So solid, we will write simply as an S. And if you have a solute in an aqueous solution, for example, sodium chloride in water, you will have something like this, AQ, to indicate aqueous solution, or again, a solute in a water solution. Okay, we're not done here still writing this chemical reaction, and that's because by the conservation of mass law, you actually need to have the same number of type of atoms in reagents and in products. And here that's not the case. For example, as written, the reaction has 4 hydrogen atoms in reagents, but only 2 in products. Okay, so this is what we call balancing the reaction, which we're going to learn in a subsequent video. Okay, so now the reaction is balanced, and again, this is very important. You need to have the same number of types of atoms in reagents and in products. And you can see how in this case, carbon atoms you have 1, reagents 1 in products. Hydrogen atoms you have 4 in reagents, 4 in products. And then oxygen atoms you have 4 in reagents and then 2 and 2 in products. So now the reaction is balanced and the reaction is correct. Okay. Now, because the atoms don't get formed or destroyed, they only get transformed. And chemical reactions really can be understood simply as a reorganization of the bonds, of the connections of the atoms. Right? If we think about methane, methane is connected to you have a carbon atom connected to 4 hydrogen atoms. O2, you have 2 oxygen molecules bonded to each other. We still don't know if the bonds are single or double, as I'm writing them here. That's something that we learn along the way, but that is not important for what we're trying to illustrate here. CO2, you have the connection between carbon and oxygen like this, and water, you have something like that, and there's 2 of those. Again, these are the structural formulas of these compounds, and again, what we're trying to see here is that the only thing that really is taking place in a chemical reaction is a reorganization in the way that the atoms are connected to each other. Right? So in reagents you have 4 carbon-hydrogen bonds, but in products you don't have any of those bonds. That means that these bonds have been broken and new bonds have been formed. That is what happens in a chemical reaction. But again, the atoms themselves do not change at all. Okay, it's just the connections of the atoms that change. Now, when we have a chemical reaction written like this, there's a lot of information that this conveys. Okay, for example, we know that we can take a molecular view of this process. Okay, at the molecular view, this would mean that one molecule of CH4 that contains 5 atoms, 1 of carbon and 4 of hydrogen, is going to react with 2 molecules of oxygen to generate 1 molecule of CO2 and 2 molecules of water. Okay, that happens at the molecular level. But if we're looking now at the macroscopic level, at the laboratory scale, then we can actually say that the same thing happens with moles. Okay, if you get an Avogadro number of methane molecules, that is 1 mole, this mole of methane is going to react with 2 moles of oxygen to generate 1 mole of carbon and then 2 moles of carbon dioxide, and then 2 moles of water. Okay? All right, so the relative amounts of each is established by these coefficients. Here you have 1, 2, 1, 2, and that is what we call the stoichiometric coefficients of reaction. That's going to be extremely important as we move forward and we try to do the following type of calculations. For example, if we write this reaction and say, well, if we react 1 mole of CH4 molecules with 2 moles of oxygen molecules, how many moles of products will we get? Or how many moles of CO2 or water will we get? Again, that is completely dictated by those stoichiometric coefficients. So they play an essential role in all the calculations that we're going to be doing. Okay, so we've seen how chemical reactions can be envisioned from the molecular level. We've also looked at the mole level, the macroscopic level, and ultimately we actually also want to work with this in terms of mass, right? So the goal would be, well, if I mix, say, 10 grams of methane with X grams of oxygen, what is the mass that I will get of CO2 and water? Those calculations can also be done, because notice that moles and mass are related by the molar mass. Okay, so the molar mass of methane is equal to about 16 grams per mole, and then the molar mass of oxygen is equal to about 32 grams per mole. You have 2 molecules of oxygen, so that will be the total mass. Then CO2 would be 44 grams per mole approximately, and then water is about 18 grams per mole, and then you have 2 moles of water, so that's what you get. Right, so again, notice that is with a molar mass, we can convert our transformations from moles to mass directly. We can say that 16 grams of methane are going to mix with 2 by 32 grams of oxygen, so 64 grams of oxygen, and when that happens, the reaction should produce 44 grams of CO2, and then 2 by 18 is going to be 36 grams of water. Okay, and the masses and reagents and products have to be exactly the same by the law of mass conservation. Okay, so this is all that a chemical reaction provides. In the next video, we're actually going to learn how to balance correctly chemical reactions.